Good day, class. In this lesson, we'll be finding all of the zeros of a given polynomial, or we'll be given roots and asked to find the polynomial. In this first example, we're asked to find a polynomial function. And obviously, we've been given a zero. That one particular zero is 4i. So we know that this zero is an imaginary number. Well, by the complex conjugate theorem, mathematicians before us obviously have discovered that if there is one complex zero for this particular polynomial, then there is also its conjugate will also serve as a zero. So based on that information, we know this polynomial has to have at least two zeros, both the given 0, 4i, and the presumed conjugate, negative 4i. With that information, we will then assume we can write this polynomial in factored form, binomial factors. And so we will, of course, assume that both of these zeros can be substituted into this binomial factor as such. And so with this, we can simplify, we can multiply, and then simplify again, or you may have recognized this line as difference of perfect squares, the x plus 4i times that binomial times the x minus 4i, and recognize that as a difference of perfect squares, and then just go ahead and write that as x squared minus 16i squared. And then note that I squared, of course, is the same as negative 1, so we really have x squared plus 16. Now, notice in the original problem, we're asked to find the polynomial function of lowest degree. So, of course, there could be many polynomials out there having a zero of 4i among its zeros. However, finding the polynomial function of lowest degree, we see that we can do that given only one zero. We can manipulate this thing and sort of work backwards based on the knowledge that we have. And this is what makes mathematics so beautiful. These things fit together like puzzle pieces, and we can come to a final analysis. So the polynomial function of lowest degree, having rational coefficients, and a zero of 4i would also have a zero of negative 4i, and that particular polynomial function would be f of x is equal to x squared plus 16. In this example, we're given a polynomial and we're asked to find all zeros. Now, when we say all zeros, apparently we're talking about all the rational zeros, numbers that can be written as numerators and denominators, and all of the complex solutions, zeros, and the irrational zeros. So we can focus initially on the rational zeros because they're quite easy to find by the rational root theorem, which says we can take the constant term and all of its factors. Notice how in that numerator I have the factors of our constant term there. 1, 2, 3, 6, 7, 14, 21, 42, all of the factors of that number, 42, both positive and negative, and I can divide it by all of the factors of my leading coefficient. The leading coefficient apparently is 1, the coefficient in front of that x raised to the 4th power, both positive and negative. And so notice how in the numerator are what I refer to as my p's, and if you study it in your textbook or study the rational root theorem, we often refer to those as p, and then the denominator, we often refer to those as the q. So if you studied that, you'll find that common notation. But even so, you're dividing all the factors of your constant term by all the factors of your leading coefficient, and this will present all of the possible rational zeros. So if I have all of the possible rational zeros, then I know that somewhere in that list of my actual rational zeros exists. And it's not always terribly easy to identify all of the factors of either the constant term or the leading coefficient. So I use my calculator to do that. For 42, I just popped 42 divided by x in my y equals, and I looked at the table for that and just scroll up and down and look for my whole number values, because that is very helpful to me to save time rather than sort of playing with, sometimes those numbers can be pretty big and nasty on the end, or that constant term. So I use my calculator to determine that. Once I have all my possible rational zeros, and you see here I've sort of listed them out in case the first representation didn't make so much sense, then I can use my calculator to determine which one are my actual rational roots by checking to see which one of these values actually make 0 if I substitute them into my original function. And so I discovered if I substitute -2 into my original function, I'll end up with a 0. If I substitute -3 into my original function, I'll end up with a 0. So you can do that by synthetic division, or you can do that by using your calculator. So I used my calculator, I entered the function into my graphing calculator under y equals. I scrolled up and down and discovered that only the values of -3 and -2 were the only ones that gave me a y value of 0. So you can scroll up and down among those possible zeros and discover that only the -2 and only the -3 will make an actual 0 for this particular polynomial. So with that, I know that among my possible zeros, I have my actual zeros discovered, and I'm going to take those actual zeros, -2 and -3, and I'm going to use synthetic division to draw out the other factors of my polynomial, because notice how I'm factoring my original polynomial. If you look down in my third line where I have f of x equals x minus blank, close parentheses, open parentheses, x minus blank, I have all my binomial factors there getting ready, because notice this is a fourth root polynomial. X to the fourth power is my highest power. So it's important to me to think of this in terms of 4 roots or 4 binomial factors if I factor this thing out. So I want to deal with my -2 first to find out if I factor out my -2 factor, my x minus that -2, if I factor out that factor from my polynomial, what polynomial is left? So I'm going to do that using synthetic division. If you don't recall synthetic division, it sort of looks like this. I drop that 1, I multiply -2 times 1, I put that outcome underneath the -4. Then I add those two, the -4 and the -2. I come out with -6. I multiply the -2 times the -6. I end up with 12. I I add those two, forgive me, or combine those two, should I say, and I end up with -34. I multiply again. I combine those terms. I multiply again. I combine those terms, and I end up with the 0, of course, because this does fit perfectly into, -2 does fit perfectly into, or the factor fits perfectly into my original polynomial, leaving me with, if you notice my outcome here, I've got 1x to the third minus 6x to the second minus 34x minus 21, if you'll sort of follow me along that path. And then now I can recognize one of my binomial factors has been managed. I've pulled that out, and then now I need to deal with now I have what's left behind. Once I factored this out of my original polynomial, I have 3 additional binomial factors remaining. One of them for sure I know is -3. So I'm going to deal with that based on what remains here in my, after following my synthetic division, what remains of my polynomial that hasn't been factored out. Because now I've already factored out that x minus the -2 factor. So now let's do synthetic division based on this -3 and what remains. So we'll divide -3 into this polynomial, these polynomial coefficients, and notice what happens. If you just study what I've done here, same thing I did in the previous example or in the previous portion of the problem. I just factored out, or I divided my factor of -3, and I discovered that I have what I have left. And so my x squared minus 9x minus 7 is what remains after I factored out that -3. So notice how 2 binomial factors have been handled, x minus -2 and x minus -3. I have 2 binomial factors remaining. Because these are not rational zeros. I've already identified my rational zeros. I know they're going to be complex or they're going to be irrational, which are sometimes difficult to handle. So for that reason, I'm going to take a look at this thing in terms of the quadratic formula. Recall how we have the, I'm going to deal with x squared minus 9x minus 7. Where did I get that x squared minus 9x minus 7? Remember, I got that from what was left over after I factored out using my synthetic division. I factored out the -2 binomial factor. I factored out the -3 binomial factor. I simplified those, and all I'm left with is the x squared minus 9x minus 7. I use that, set it equal to 0 to find out when is this factor equal to 0. And so whenever we do that, we can use the quadratic formula. Notice how I've used the quadratic formula there to solve, to find out what is the value of x when x squared minus 9x minus 7 is equal to 0. And you can see how I've used the quadratic formula there, and it yields the, in the final analysis, it yields the values of x when x squared minus 9x plus 7 is equal to 0. Now I have revealed all the zeros for this particular polynomial, both my rational zeros, -2 and -3, and it turns out here I end up with irrational zeros, 9 plus the square root of 109 all divided by 2, and 9 minus the square root of 109 all divided by 2.